Hello everyone, it's October 28th. A bit late today because I fell into the rabbit hole of code golfing. That was something interesting. There's a language called Jelly that's very, very interesting. Or somebody say it's just, extremely unnecessary. But it's fun. Code golfing is fun. And then the language of Jelly, and also there are other ones like Husk and Japt. These are all ways to shorten the code as much as possible. Basically, use symbols, exotic symbols to represent a macro. But I think it's worth looking into if I have time. All right, that's what we have today. So number 15, we've done it more than two times, more than once, I think. Let's see if we can hammer this. Oh yeah, look at this. Oh, look at this. I start from 2018, August 2018, and the track record doesn't look nice when we start, all right? So I tried it one day, couldn't do it. The next day, tried again, still couldn't do it, and got accepted with terrible, terrible runtime. Keep trying, look at all the tries, keep trying. Oh my goodness, And eventually, I think this is the final one. I arrived at a good one. All right, that's the first journey. Second journey, 2020. It's actually just last year. Again. Wow, this is not an easy question. Like 2 years, I still couldn't do it. All right, let's see. What the hell? Is it hard, huh? Oh wow, look at the likes. I've never seen something as liked more than 10,000 times. Alright. Give an integer array, return all the triplets such that they're not the same equals to 0. Yeah, I think I remember the solution. I even remember there's a generic solution of k-sum, but this is 3-sum. And we know there's a 2-sum. 2-sum is easy, right? And 3 sums, if I remember correctly, it's going to be 3 pointers. I think it's 3 pointers. Let me see. So we're going to have a front pointer, a back point. Well, it's actually not front and back point. So we have a front pointer, right? So say if I want to take -1, then it becomes a 2-sum problem to find these that will add up to 1, right? That's that. And the solution set must not contain duplicate triplets. Okay. Anyway, so yeah, if I lock down -1, then I want the remaining to give us, it's a 2-sum problem to give us 1. So if it's a 0, I need a 1, right? If it's a 1, I need a 0, but I already do it. Wait, hold on. The numbers, they didn't say, the numbers can have duplicates, right? Yeah, I think the numbers can have duplicates. So it's a little more complicated, but it's just, yeah, duplicate is fine. Just we use a counter, right? So if it's a 0, I need a 1. So boom, we have it. And if it's a 1, I need a 0. How do I eliminate that? If it's a 0, I need a 1. So I can create like a tuple, all right, to see which one we have taken. 2 will require -1, so we have it. And -1 will require a 2. Okay, and -4 requires a 5, but we don't have a 5, so that's it. So we actually already found it. So now what? Now I say it has to be 0 and no minus 1. So 0 needs a 0, so we need to find a 0 in here. Now we have 1 and minus 1 again, and that is a duplicate. I mean, if you think about it, if we use tuple to handle duplicate, this problem is not that hard. And all we need to do is make sure that when we create the triplets, it's going to be sorted, right? If it's sorted, then we can turn that into a unique tuple, so we can handle it that way. Yeah, I think that shall be, so yeah, like 0, and we only consider the remaining, right? If it's a 1, we only consider remaining, has to be 0, nothing is 0, 2 has to be 1, nothing's 1, and that's it. So, in that case, I just try this. Maybe this one works. I honestly don't really remember how I solved it in the past. But that's how I will solve it right now. Okay, let's go here. All right, threesome again. I need counter, right? That's what I need. Wait, do I need counter for this? I mean, this is the question: is how do you know that when you pick a value, I can decrease these, right? Every time I move forward, I decrease these, so I know what the remaining look like. Yeah, I think it's useful. So let's say from collections, let's get a counter, and let's get a counter equals to counter nums, right? And now the result has to be a set, right? It has to be a set, and I'm gonna say for n, for in, enumerate nums, right? I'm going to take the first I. So I will say the target, right? The target is going to be 0 minus n, right? Because that's what we want, 0 minus n. So now it becomes a two-sum problem. Right? So we're going to say for j in range, so I cannot take, so I plus 1, all the way to, let's get a length as well, n equals length nums. So let's be n minus 2, because that's n minus 1, that n minus 2, so we can only take up to this. Oh, actually, no. This we can go all the way to the, okay, go all the way to here. Hold on, let me think. If we are ignoring, right, we are ignoring, then it should go all the way down, right? Because every one, we can try. Let me think. Every value I can try. If I tried it, right, then I'll have two values. Then as I go through, I hit another value, right? But if this value has been used before, yeah, then we don't have to. Let's just, yeah, this is going to go through every single one. Actually, hold on. We don't even have to go through every single one. I think going through half. No, it's not sorted. We cannot go through half. We do have to go through every single one. So I think we do go through every single one. It's Yeah, we don't go through every single one. So we do go through every single one. And as we go through every single one, we need to keep track of what we have seen already. So, for another thing is counter n equal minus equal 1, right? So we're going to reduce the counter so we won't count this one again. And also, we're going to set the scene equals a set, right? So, do we say scene equals a set? Yes, it's fine. I mean, the whole point right now is we have a value and we see if the other value is in there. If it's in, we put it into the scene, right? So when I hit that value again, we don't do it. We don't do it again. But we don't want to change counter, because if we change counter along the way, that will be a bit difficult to reason with. So okay, so here's the deal. We have a target for a j, so we say if target minus nums j, right? If this is in, no, it's gonna be counter this has to be larger than 0, right? If this is larger than 0, and nums j is not in scene, then in this case, we are already considering, now we still need, so then we say res dot add, right? We're going to add a sorted array of n, nums j, and target minus nums j, right? After we added it, we can say scene.add nums j as scene.add target minus nums j. So actually sorted this, it has to turn into a tuple. Right, so I have to turn into a tuple. Sorted and turn into a tuple. So we add this, we do all this, and the next one coming in, put a check, and also see if it's in scene. So once we're done, we can go on to the next one. The next one. And then we can return list, right? List R for R in res. Yeah, let's see how this one goes. So we have this. And the solution is this. All right. And we also, the next one is empty, return empty. Next one is 0, return empty, because it has to be 3. Okay. Nums, 3-sum nums. Yeah, this is correct. I mean, we can. Wait, maybe we can use sorted. Does that help? It helps. Okay. Well, let's try it. Maybe this is sufficient. Let's try it. Nope, we got a wrong answer. Input 0, 0, output. How is that possible? Hold up. Indeed, right? You think think you've done this enough times. Hold on. So what is the issue? So I have this star, right? So the target would be 0, and I already decremented by 1, and then I go inside. So we're starting from here. Oh, I see. Holy guacamole. Yeah, that is the problem. Maybe we can do better. So maybe it's gonna be this. Yeah, let's do even better. So what we want, right? What we want is counter, right? We want counter. Yeah, that's definitely larger than equal to 0. It's after we take. It's the duplication issue. So after we take nums j, we need to know that counter this new value is still larger than 0. How do we express that? Well, let's do this. That's just minus. So counter nums j, decrement, and then I check, right? And the check does not include anything, and at the end I just put it back, right? Nums j plus equal 1. I just put it back. This one will solve it. All right, try this. All right, you asked, I'm gonna try it. This one should be 0, 0, 0. Yep. Try this one. Submit. Let's see if I don't see the test cases. Oh, it doesn't seem like. Was that timeout? Oh, we got it. But with ridiculous runtime. Jeez. That's even worse than I started with. What the heck? Oh, that was terrible. That was terrible runtime. Let's see. All right, we didn't record this one for sure, but I did not improve at all. Well, I did improve because 2 years ago, I wasn't able to solve it for more than a day, and a year ago, I wasn't able to solve it for 2 hours, more than 2 hours, right? And today I was able to solve it, let's see, how long? 18 minutes, right? 18 minutes, but with a terrible runtime. Look at this. Oh, I don't even want to see. Jesus, you can't even see it. Right? You can't even see it. So it's pretty bad, right? It's pretty bad. I thought I have it. I thought I knew how to do this, given that this is my 3rd try at this problem. Unfortunately, although I passed the online judge, the runtime was abysmal. Probably, I think, is that double B or double S? I think double S, right? Abysmal. So the ideal is to keep one value secure, keep one value, and check the remaining nums Check run it for a two-sum problem. Now the time, lots of time is spent. A lot of time is spent on preventing duplication. Yeah, so that is something we need to work on, right? A lot of time is spent on preventing duplication. And the overall runtime is O(n) squared, I'm pretty sure. It's O(n) squared. And got a 7652 milliseconds. Oh, this is very bad. I think it's O(n) squared, right? Yeah, it is O(n) squared. That's O(n), that's O(n) again, O(n) squared. Everything else, you can amortize it to O1. Okay, can we do better? Of course we can do better. We did a 700, right? The 700 milliseconds. So definitely we can do better. How do we do better? What if we, I don't know, I remember this is a two-pointer problem. Now that's something in my head. So what if we just have 2 pointers? And then one at the front, right? And one at the end. So with 2 pointers, we're just moving in, right? Basically we say if we take this and this, what are the likelihood, right? And how do we move in? We move in once. Oh, hold on. Hold a sec. I can sort it. I mean, the actual runtime could be O(n) log n. What if I sort it? I never thought about this. Let's sort. Yeah, let's sort. 0, 1, 2. Okay. Now I sorted it, right? Then I can, if I sort, I can go front and back, right? So I say I want front plus the back, and that's -2, right? And we need a 3. We can look for a 3, but there's no 3. 3 is too big, right? So if that's the case, I think the magic is about to happen. Like I need a 3, -4 plus 2, the smallest plus the biggest. And that requires a 3, but we don't have a 3, right? Because the largest is 2. Therefore, the smallest is too small. So I need to move the smaller forward, okay? Now I move the smaller forward, now it's -1 plus 2. That gives us 1, so we need a -1. So we search if it's a -1. Yes, we do have a -1, so we're good. So that's one solution, -1, -1, 2. Okay, so it's good. Then what? Well, then, let's say we just keep moving the left pointer. Okay, we move the left pointer forward because it's good. So we keep moving the left pointer. I mean, I can move the right as well, but I don't think it matters. So we move the left pointer forward. We had another -1, so we need another -1. That's a duplicate. All right. Well, we can just keep moving until, yeah, we can keep moving. We can reduce all the duplicates. We'll move all the duplicates. Yeah, if the left pointer, we get rid of all the duplicates, then I move forward, move to 0. Now we have 0 and 2, right? And 0 and 2 give us 2. I need a -1. No, I need a -2, but we don't have -2. I'm missing a solution. That's fine. We need a we need a -2, right? But currently I'm pointing at a 0. So it's -2, which means it's too big, right? It's too big, so I need to move the right pointer forward. Now I have a 0 and a 1. Yeah, -2. Why do I think it's too big? because I don't have -2. And hold on, I feel like I'm almost there, but let's do some logic. And 0, 1, we get another 1. All right? Okay. -2. How do I know when to move which pointer? Right? Like, start and end. We're always trying to move as much as we can. Right? We just say, if the next one is the same, then I just move, I just move, I just move, I just move. But eventually, if everybody's the same, then these two will meet each other. And that means everything is the same. Okay? Because the point is to have two values. Right? We set two values, and we're looking for the third one. And because there could be duplicates, so every time if it's the same, I just keep moving, and if it's the same, right? And I keep moving until we enter a value that's not the same. Then we stop. Are we always moving on the left? Yeah, because we start with the smallest plus the biggest, right? If the smallest plus the biggest, then the value is within the range, then we can try to find it. But if I cannot find it, how do I know if this value is too big or too small? I mean, if the value is like something in between, it just doesn't hit, which direction should I go? Yeah, which direction should I go? And this one, -4 plus 2 is -2, which requires 3. It does mean that it's too small. So it makes sense I need to move the left pointer. Now what if I have, let's say, a -1 at the start, right? If it's a -1 at the start, then I'll say, okay, value is 1. I can find it's inside. And then what? Right? And then what? It's a toss. We can move the left, we can move the right. Let's say we move the left, and then we're going to try it again. And then we're missing, and we're missing the chance for the right side to move in. How do I ensure both the right and left side can move in? Man, this is not trivial. I thought this is very trivial. Think again. Yeah, I think sort is the way to go. So we sorted first, right? And then I sorted first. I got 2 pointers. I do believe it's a 2-pointer problem. And then this has given us a certain value, certain target we need to hit, right? With one value to hit the target. And it could be, if it's too small, which means if it's smaller than the current pointer on the left side, then we need to move the left, which means the current, no, it's only the right, the current sum is too big. So we move the right. If it's too large, then we move the left. That's all good. But what if it's landing somewhere in the middle? Right? What if it's somewhere in the middle? if it's somewhere in the middle, we try to find, right? We try to find. Now we can let's say we binary search it to get that position in, right? Let's say we can get that position in, and based on that, yeah, it could be any position, right? It could be any position. We say if it's in between some values, right? Then, like if we don't fit, but it's in between some values, how do I move, right? If I move, which means if its value is smaller than something and bigger than something else, right? And in order to fit, I can move both directions. I can move the left. If I move the left, then the third value will move to the left. If I move right, and it will move to the right. Yes. But still, there's no clear direction to move. Hold on. How about we go back to what we have here? Can we do this like, oh, it gotta be O and log n. We're sorting already O and log n. So I take the first one, and then I look at the remaining, right? If I take the second one, so let's just say I take the first two, then I need to look for, oh, there's nothing, right? Then I know it's, I take this, then I take this, then I take this, and I take this. Like everything will fit to -4, but none of them does. None of them does. I didn't use the sorting. So if it's a -4, right? And we need a large value, right? Oh, hold on. If I sort, then it gotta have negative values, right? So if the smallest value is a positive, then that's a moot point. Then we don't have to go anymore. Okay, that's a discovery. So the smallest value has to be a negative. Okay, so we have a negative value, then we need a positive value. Then we look on the positive side, right? And oh yeah, like if the largest value is smaller than 0, the smaller value is larger than 0, those are a moot point. We don't have to do anything. Okay, but now we have both negative and positive to start with. And we know there has to be some negative plus some positive, except from if it's like zeros, right? Okay, so in that case, we have some negative and some positive. We can compute, right, the sum, the smallest and the biggest. Yeah, because, yeah, we can do, yeah, smallest plus the biggest. We'll get a value, right? And then we find the value is too small, right? The value is too small. Now, if the value is too small, then we need to move the small upward. Okay, so we need to move the small upward. Now, what if the value is, yeah, it's still the same problem. The value is in between. Now, which direction to move? Hmm. One is 4, I need 4, right? I needed this one to give me 4. No, this one give me 4. I need this one to give me 5. There's no 5, so no, this one doesn't have 5. And technically we can also remove the duplicates. Yeah, I just don't know which direction to go. If I find a good one, right? If I find a good one, and we can look into the counter to see, okay, we have one. And let's say once we have, let's encounter this, including this value, and including this value, right? That is deterministic. Like if we have a pair and we find, and then we can just ditch it. We can move this, or we can move this. Man, I don't know. I don't know. I need some hints. I think it's 2 pointers, but I got stuck. Let's see the hint. Add up to the given value. If we fix one of the member, it's a two-sum. Yes, I know. It's a two-sum problem. The two-sum, if we fix one of the value, we can scan entire to find next value. Yeah. Where value is the input character, a parameter. We change our array sum. This is, yeah, that's exactly what I did here. Without changing the array, can we use additional space somehow? I did all of these. I did all of these, and it gave me a very bad runtime. That's why I don't know what to do. Right? This is exactly what I was doing. You know what? I want to check my previous answer. And my current answer. I mean, for one thing, the test case increases from 313 to 318, right? So that is more. But other than that, I did do a lot of checking here. I mean, maybe I don't do this, right? If I don't do this, I don't think it's gonna speed up. I'm gonna try. Let's see. Oh yeah, let's see if I don't do this, right? And just check this. So we don't have to set this every single time. We're still gonna pass. I want to see if it's gonna be any faster. Maybe. And maybe the extra checks are not really saving us time. Let's see if this one will be any faster. I mean, another thing is we don't have to. Yeah, that's fine. No, I don't think it's any faster. It's probably even timeout. Honestly. Nope. No, this is not faster. This is not faster. What if we add some checks, like some, let's say if max nums is smaller than 0, right? Or min nums is larger than 0. Then we return this. Or if len, right, nums is smaller than 3. Right, len nums is smaller than 3, or max or min, and then we return this. Let's see if this will make it a little bit faster. Nah, not really. Not really. Nope, nope, this is not. So that's not the trick. Alright, let's see what the trick is. What the heck? Alright, we have a counter. Sorting, this is what I thought. First two uniques, The first larger than 0 would break. That is true. The third, yeah, you see that? It's a front and back. It's a front and back, right? It's front and back. And what? Second is 0 minus if third is smaller than 0, okay, or second is larger than third, then we break. So yeah, we form in an order. Okay, let's just hint to here. So we did think about everything that's been said so far. And we have a breaking situation, which is the third one. Okay, so 1, 2, 3, they're in order. So we're saying 1 must be negative, third must be positive. Exactly. So if the third is negative, that's a no-go. And we have them in order, so the second one must be smaller than the third one. That's okay, yeah, that's true. So that means, right, so we have the first and a third, right? Or first and third, and we need to compute the second. And we're saying if the second value is supposed to be in the middle, right? But it's actually to the right, or maybe to the left, doesn't really matter. Then, yeah, if the second value is not in between, then we stop the search. What does that mean? That means that the second value, if it's too big, that means the first and third value are too small, right? They're too small. So, because we're converging to the middle, so they're not gonna work. Or it means it's too big, right? If it means it's too big, that's also no good. Okay, so that works. Yeah, that's exactly what we got stuck. So now we have a second value which is somewhere in between, right? And I said if the second value is larger, that means it's too big, right? There's no way, right? If it's too big, but hold on, that's not what I thought. I thought if the second value is too big, then I just move the first value. That's what it says. It will break. Oh, hold on, it breaks. Oh, it breaks different. It's hold on. So what I'm saying is I will stick the first one and move on the third one. The third one will keep moving, okay? The third one will move, and each move I will compute. Isn't this the same as this? No, it's not, because we have early stoppage. This one we have to go through the entire thing because we didn't sort. But this one we sorted, so We know the first, we know the last, so as we go through, if anything that's out of the order, then we can just kill it. Okay. Okay. And in my idea, first and the last, right, I'm moving the front, which is also fine if I'm moving the front. So if I move the front, right, we're trying to find one, and we'll definitely find something. And then we move this, move this, move this, until a point where the front becomes positive, right? Oh, I think I know. This is to maintain the order. So everything we find will be unique because it's in order, right? It's in order. So everything we find will be unique. So I move the front. So this is still O(n) squared. It's still O(n) squared. I just move the front. I think a couple of things that's different is I'm moving the counters instead of moving. Hold on, I think we can change this to make this run faster. So instead of going this way, why do we go this way? Exactly, why? We don't have to go nums. We already create a counter. So we shall do the counter way, right? Yeah, that may be a time save. Let's see. No sorting. Let's just say we do count. Hold on. Let me redo this. Yeah, I think the key is the counter. We remove the duplicates. Let's see. Let's say counter, right? And we just say for I n. Oh, but we cannot iterate through the counter like this. Therefore, we have to sort the counter. That's why I call it a uniques sorted counter. So I'm going to go from front. So for I n enumerate uniques, right? I'm going to go through every single one. And if n is larger than 0, then we're going to break, because that's not going to do us any good. Otherwise, then we're going to go from back to the front, right? And say for j in range, from back to the front, n minus 1, right? Minus 1. Actually, not minus 1, so because j, I cannot go. The last one j can go is I plus 2, right? As I plus 2. So I cannot go to I. Oh, it's actually I can go to I. It's fine. I cannot go beyond I. So we're gonna do I can go to I, but cannot go to I minus 1. So it's gonna be I plus 1. Because this is gonna be minus 1. Wait, hold on. No, it's actually I minus 1, right? I minus 1. And I can go to I, but I cannot go to I minus 1. That's why it's I minus 1. So that's j. J is going to go from the back to the front, right? And every j, we can compute now we can compute a target. So the target is going to be 0 minus n minus uniques j, right? 0 minus 1 minus unique j. Now we need to know if the target exists, right? Now there are other possibilities. So we want a target to be in between, right? So if the target is already, because the j is moving to the left, right? Which means the total sums becomes smaller. So the target is become bigger. The targets become bigger, right? Every time j moves, the target becomes bigger. So if the target is already too big, that's a no-go. Therefore, we say if uniques j is smaller than 0, because we need unique j to be positive, to larger or equal to 0, and n to be smaller or equal to 0. That's the starting point. We cannot have the larger value to be smaller than 0. So if this, or say target, is larger than uniques j, if target is already larger than uniques j, and will keep growing, the target is keep getting bigger, then there's no way, right? There's no way we can find it. So we need the target to be in between n and uniques j. So if these situations, then we're gonna break, which means we're gonna redo, which means we're done with j. With j cannot become even smaller. Okay. So if not, now the target is in between, right? Now we need to see if the target, we can do it. So how do we do? So we need to check if target is in the range, is inside the uniques. How do we check it? So we're gonna say condition is counter n minus equal 1 counter how do we even know uniques j is possible? Well, unique j, unless I'm saying the unique j cannot take, oh yeah, it is unique. That's why it's possible. It's unique. It's unique. So counter uniques j also minus 0, 1, because we're taking these two values, right? Then we want to see if counter, after we do this, if counter target is still larger than 0, that means we have a result, and we don't have to do that as well. So we have a result. We can say res.append, and we can also do it in order n, target, and uniques j, right? If that's the case, then we do. If not, then we don't, and we just put these two back, right? We put these two back, plus and plus, like backtracking, right? And eventually we're gonna return res. How about this? I'm gonna try to run it. Oh, we have duplicates. I think that is the issue. We have duplicates. Why will we have duplicates? This should not be possible, because n must be smaller than. What is the issue here? The issue is target has to be bigger or equal to. So if this and, I have to do another and, right? And target is larger or equal to n, right? It cannot be smaller than n. Then we pass. All right, let's try this one. We used the previous. All right, let's see. So I can delete this. Go. Much faster. Much faster. Yeah, that is the solution. So this is the solution. Well, I had to check my solution a year ago to obtain the insight. So I got very close. I got very close to this solution, but I was stuck at trying to make it O n log n. This is not O n log n, right? This is, technically speaking, wait, is this O n log n? I fix this and I go this one by one, right? And I fix the next one and I go one by one. I think this is still O n squared. It's trying to make the solution O n log n, but in fact, the correct solution is still O n squared, right? But with much, I mean, the n is smaller, right? The n is smaller, but with much smaller n, since we are using uniques. Sorting is important. Sorting is important because it allows us to create unique triplets as we search for them. Yeah, that's important, as we search for them. Create unique triplets as we search for them, because because it allows us to create unique triplets. That is, we can create triplets that are already sorted. All right. Another benefit of sorting is that when we can determine on the min and max of the potential of a potential triplet, and then as we change, as we shrink on the max, we can break out whenever the max drops below 0, or the third value, or the median value. The median value becomes bigger than max. This saves a lot of time. So yeah, so this one runs in, I think it's still O n squared, right? It's still O n squared, but it runs much faster. 1732 milliseconds. I mean, it's not going to be as fast as the previous record because the number of test cases increases, but increases 5 test cases. And now you see this, I use all these to compare, which here I improved by just do the minus, right? I mean, yeah, it's fine. I will have to compare it to the third is not equal to second. No, I think this logic is not as good. I like this logic, which basically just like a backtracking, right? So we say we count these two, and want to see if this is still good, right? If it's good, then we're good. And because it's unique, right? Because every value we go through is unique, so they must exist. So n and uniques j, they both exist. So we only need to check for if target exists, and we use this to ensure, right? Everything is unique. Wow, this is harder than I had thought. Yeah, I thought we were gonna go a breeze, but we did finish, but it's bad. That's pretty bad. All right, that will be it for today. I'll see you guys tomorrow. Adios.